Good. Yeah. Oh, these look kind of like. I love these. Oh, sugar. I really need some sugar right now.
Sugar.
Where's your true role? Like, is it are they process covered?
Yeah, I'm basically closed up. For some reason they can't research my
So I guess.
that's basically
I
think so.
It looked like you were shooting, didn't it?
I was about it. And research
I think there was only one day.
Was the early one? Oh, is that the sheet I think it's like a baby?
Different are they
Might still be here.
styles?
I think they have a
That's great.
like lost a lot.
Earlier, but
Yeah, they had a
Yeah.
Question mark one was the one we ended up canceling.
I don't know.
Yeah, this one's very powerful. So it's in commercial world with others. So we find that everyone asks how to use it. Yeah, like whenever someone sees iPod, they will like. Okay, that sounds nice. Okay, that sounds fun. Yeah. I was gonna say, like, that's about, yeah.
Actually based on cookies.
Pretty much. I mean, no, what's the
Sugar today.
If you have to get there, there's something wrong. Right? If you wanted to do it high all the time.
These ones are like, they're alright.
How are you?
That's okay. Yeah, no worries. Yeah. So normally messages come through I know. Yeah, so half an hour break.
Yeah.
So I hope there's enough handouts now.
Oh yeah.
You know, actually I tried. It also told me 2022.
Right.
Okay, we would like to start.
No learning.
So today we'll talk about artificial intelligence, machine learning, and as usual, it's not a lecture, it's more of a discussion, so just give us sort of incentives to speak, and then every person might speak for a few minutes and ask you questions. And this is a very exciting frontier, so thank you all for coming. And the speakers today are listed over there. We have a visitor actually from the Flatiron Institute, 5 hours away in New York City, and it's great to see you. So Chirag, would you start or Carol? Who is starting?
I just quickly introduce Chirag. So Chirag works at the intersection of ML and cosmology. And because I already ran it enough last week, I thought it'd be good to hear someone else's run.
We can hardly hear you, so the question is there a microphone over there? Or?
There is a microphone, yeah.
Yeah, so why don't you use it and I'll close the door also. Please go ahead.
So I just want to say before we start that I understand that many people here are not experts in ML, but I think it's been around enough for people to build an intuition of when it is useful and when it isn't. So please speak up. We really want to hear your opinion. So don't be afraid of saying something that might not be right. Just feel free to say anything. And kinds of that, yeah. Sure, kind of.
There should be an on-off button at the top, and then you just.
I had trouble getting this to work a few weeks back. I wasn't sure how to do it.
I'll try to speak louder. I'm clearly not good with machines.
I thought it was supposed to be also streamed because someone you requested it.
Yeah, that's true.
It's supposed to be streamed, so you need the microphone.
Sorry.
Yeah, we can.
That's one thing AI hasn't solved yet.
Is this working?
My goodness.
Is this working? Yeah. Okay. Okay. Great. Okay. So hi, I'm Chirag. I'm from Flatiron Institute, and we'll be discussing about machine learning in astronomy and if it is a success story. So before we start, I kind of wanted to just get a sense of how many people here do use machine learning in science or astronomy. If people can raise their hands and those things. Okay, so we have some people who don't, some people who do, so that's a good split for this. I wanted to start with a disclaimer first, that some of the things that I would say, I'm a cosmologist, so there'll be some personal biases and coming from cosmology side about how things work there or not. Some of the discussion will end up being subjective just because of the nature of the topic, so we should be respectful about that. And sometimes I might adopt a slightly pessimistic or critical stance just to motivate some discussion in that sense. So, I think. Okay. Right. So, I started this when I was making the slides. I did what people generally have started to do nowadays, is go and ask ChatGPT about what it thinks about this thing. So, my prompt to ChatGPT was, has machine learning been successful in industry? And it kind of gave me this list of 12 answers telling me about different industries and how it is being used there. We would not go in detail here because this is not the main point, but if you read any point here, you would notice that each of the point here has many different concrete subpoints in this setting, showing how machine learning has been successful in different industries. Just to put a numerical value on the success, currently, AI is supposed to be $200 billion industry, and over the next 5 years, people are expecting it to be $2 trillion industry. So by some metric, you can say that machine learning is successful in industry in that sense, right? People have probably played with DALL-E at this point, but this is just to illustrate that people have been able to use machine learning to train text, images. It can now understand language. It can now understand, at least in the sense, images. It can understand correlation between the two. If you would give this prompt to me, I don't think I'll be able to come up with a picture that good, at least even in my imagination. So in some sense, it is learning something better than what most of us humans can do in this sense. There have also been success stories like AlphaFold, where people have used machine learning to solve a 50-year-old grand challenge problem in biology about protein folding in the sense. You might say that this is scientific success of machine learning and not industry, but the reason why I put it in industry here is because this was done at DeepMind and not at any university institute in that sense. And we'll touch upon this at the end, come back to this point at the very end, in a sense. Also, there have been, it's not only that it has been successful, it's also, the other thing is also the pace at which it is improving, in the sense. So for example, this is an example of people where they queried ChatGPT 3 times over a month period to draw a unicorn with ticks. And you see that even in just 1 month, the improvements in the algorithm were massive. It started from there at the beginning of the month, and it ended here at the end of the month. So the rate of improvement is also very high about machine learning in industry at this point. And finally, the last thing I wanted to point out about industry is that most of the successes here have come from something like these scaling laws, where people have found out that as they increased compute, as they increase the data size that they are training on, and as they increase the number of parameters of their model, as they're going to bigger and deeper models, they do find consistently better and better performance in this case. This is not something that's happening in science currently. Okay, so with that setup, I kind of wanted to pause here at this point and ask, has machine learning been successful in astronomy? So before we dive deeper, I kind of wanted everyone to take like 2 minutes and I assume on the sheet of paper that you have, you must have some space. So if you can write down your thoughts, you can either take one of the two stands. You can either say that, okay, it has not served anything good in astrophysics so far, and it might not be successful. So if you can give the reasons for that. Or if you think that it has actually done some good and it has revolutionized the astrophysics, and if you have some examples, I want you to think about that. So maybe like a minute to gather your thoughts.
You asked ChatGPT what it thinks about this?
That's the next slide. Right. Anyone has any thoughts on like how many people think that it has revolutionized astrophysics? If they can raise their hands.
Is there any point?
Okay, we can like mellow down the first one. Not useless, but it hasn't been as successful as we would have hoped it to be. How many people would agree with that sentence?
Do we make a distinction between astrophysics and astronomy?
Sorry?
Do we make a distinction between astrophysics and astronomy?
No.
Maybe not. No, not necessarily. But are you saying that it has been more successful with astronomy or less? In that sense.
Yes.
Fair enough. Okay. So, anyone wants to comment on any of these? Yep.
I think I do lean more towards revolutionized astrophysics, but as something that's not leading to breakthroughs in our knowledge, but they really do enable science. So in time domain, for example, even real bogus classifiers, so we get in a new image, we decide whether or not it's an artifact or real transient. Yeah, that's been done with machine learning for decades. It's pretty simplistic, but genuinely has changed the way that we find these things. So it has had a major impact, but on very human tasks.
Right. Okay.
I also think it depends on how you define machine learning, because we've been fitting lines to data for a really long time. We allow computers to do that. That's machine learning. So we've been doing that for a long, long time, and it has revolutionized astronomy. It's simplest form,
Okay. So that would be saying that things like linear, not linear, just regression, but that would be statistics sides of things. Are we differentiating between statistics and machine learning, or?
Yeah, that's really what I'm saying. I think it depends on how you define machine learning.
Okay. With statistics, I think I would personally agree. That forms the basis of almost any science in that sense. Machine learning, at least in this context, was more and when you are using some sophisticated model where you do not necessarily interpret or understand every component of the model that you're using for training in that sense. So in statistics, if you're doing inference, you're not really training it on anything beforehand, right? In that sense. So if there's an element of training involved, then I think I would quote it as machine learning, at least for the purpose of this discussion. But if you are not really training on beforehand, then we can consider it to be statistics for this end.
I think this is a philosophical point. Because
No, I agree, yeah,
when
but
we fit a line to data, we're training the line to the data.
I agree, but we have to like make something concrete for the purpose of this discussion. So that's why, in the sense, like the few next coming slides are based on that assumptions. Yeah.
Okay, I think it's, in general, it can be useful, machine learning techniques in astrophysics, or specifically in astronomy, if I can say it means quantitative versus qualitative, astrophysics versus astronomy. But I would say that at present, it's heavily oversold.
Yes.
And I think it's oversold not because astronomers are bad, it's because of the demand. It's like there's a buzzword, if you use it, you get the grant. If you don't use it, you don't get the grant.
Yep. Nice, yeah, okay. We will, there's a point that I'll try to make at the end towards which touches upon something of that, so yeah.
There is a question here. Comment.
Yeah.
Did you want to go first?
No, go ahead.
No, I was just gonna say that I think there's different levels at which you can answer this question. I think there's definitely, as Ashley mentioned earlier, there's been useful applications of machine learning in exploring data sets that are too large for us to make any sense of correlations in those data sets, and things like classification and anomaly detection have certainly led to discoveries. I think whether that's revolutionizing astrophysics, I'm not sure. But then I think we're sort of in a transition where we are sort of fed up with all those classifiers and anomaly detectors, so we're entering an era in which machine learning is starting to help us solve problems that are very hard in terms of computational astrophysics and in terms of limitations of our simulations, where we can do things like inference, or at least support physical inference on parameters. And I think at that level, that's where I see that perhaps we could say that there would be a revolution, in the sense that perhaps the way we were thinking we're going to solve those problems, but by building larger computers, might not be the case, and we could use emulators and things like that to replace that infrastructure that used to be an issue.
Karen.
Yeah, I like the idea of it is oversold, but I wouldn't call it oversold. I would say there is a dissonance between what ML has done in the world, right? Like the examples that we've been through that are just mind-blowing, and what we've seen in astrophysics. What I would argue is that we haven't seen anything mind-blowing. So it isn't solving problems we couldn't solve before at all, right now, in the real world, right? There are proof of concept applications out there for many different things, but in the real world, we're not solving problems we couldn't solve before.
Sid?
Maybe I can ask like a meta question of what would an AlphaFold moment in astronomy look like? Like, is that even a concept that makes sense?
Yeah, I mean, if you discover a new transient, or if you discover new statistics of a large-scale structure that was not employed before, because the pattern that you see in the distribution of galaxies is different from what people searched before. So things like that were not found, it's a breakthrough. It would be a breakthrough in these disciplines. And it will go beyond that. At some point, we might discover new physics this way, right? But that's for the long term.
Yeah, I guess, can I ask a somewhat controversial question of machine learning? We've talked about how you can find things in data and identify and classify, etc. Has machine learning yet helped us physically understand the universe better yet?
What do you mean by that?
As in, like, has it actually helped us increase our knowledge of physics, or has it just helped us find more things out of data that you can then use? This is a genuine question, I don't.
I'm happy to let the conversation keep going or respond.
But there is behind you a comment.
Okay, these are...
Jet, I think that's the key word, right? Because to me, I'm just starting to get into machine learning myself, but I'm super excited about it. To me, this is the example of you get a new hammer and you go after all the nails right now, right? And I think that that's the stage that we're at right now. It's like, we got a new hammer, where are the nails, right? But let's don't stop there and think about, like, if we as a community keep thinking about ways to apply machine learning to problems that we don't know the answer for, I guarantee that in 10 years, the answer will be the following. But right now, I think as Raphael was saying, I feel we're kind of like in the middle, but not like closer to the top. So,
Yeah, my genuine question was whether we have yet.
yeah.
Well, I think
Yeah.
it probably can be in the future, but yes. Yeah.
So you're suggesting that with more time, we'll probably go into the second regime,
Yeah.
even if we continue on the trajectory that we are right now.
Become more familiar with these techniques.
Yep.
And figure out what problems don't like to fall back to and in which ways.
Yep.
And me personally, I think we will revolution.
Okay.
But we're not there.
Yeah.
Oh, sorry, on this point, and maybe also this alphabetical, I think a great example is the image of a black hole from EHT. A lot of work went into a lot of physics and hardware and software development, but that was enabled by computer vision and Katie Bowman plus many others using machine learning to actually get out that image. So that's a good example, just that wasn't highlighted in the press releases. And then I think there have been examples, very few examples of finding new physics. The one I'm thinking of that I don't is the Bloom, I forget the student's name, on the micro lensing. Does anyone know what I'm talking about?
Right.
Who was it?
Kiming?
Kiming?
Yeah.
Yes, thank you. It was Kiming. They
Kiming.
found a new.
Kiming, sorry.
I'm so sorry for this person. Josh Bloom and Kiming at Berkeley discovered a new symmetry that was kind of highlighted by their analysis of microlensing events through some machine learning. I don't quite remember what they did, but the symmetry was utilized by the neural net. They kind of figured that out and then went back and found it mathematically. And so there's one.
Yeah, but that's not a new insight in physics like AlphaFold. It doesn't reveal something that was previously not understood. I mean, it's a detail.
Yeah, it's not. Sure. There is
It's not a new understanding.
I mean,
Okay. At some point, I would like to move, but maybe last moment. Yeah.
okay, I like the example that Ashley gave of sometimes there's things that are not highlighted as machine learning, but are fundamentally machine learning. Like also with some of the discoveries at the LHC, like the Higgs boson, there was a lot of machine learning that went into it. It wasn't deep neural networks, but boosted decision trees and stuff for tagging particles, and that was important, but it wasn't highlighted. So maybe the line is a little blurry for what is machine learning.
Right, yeah, that's a good point. There are different flavors of machine learning, I think, which goes back here in that sense, that at some point you might call that not machine learning, or you might not emphasize on that part, but it can lead to things. Okay, so moving on, I asked ChatGPT the same question, that has machine learning been successful in astronomy? And I asked that question twice to it, so it gave me the first 10 points the first time. The second time I asked the same question, like just copy pasting the same question. It basically gave me the same points, like it merged some of them and gave me 3 new points in this case. What do you see? And there is a natural split between the left and the right. Can people point out the natural split in this sense? Or at least what I thought was the natural split in this case? Okay.
Classification and like our actual
Essentially, yeah. So
intuition.
So on the left side, it is mostly like data processing and what Ashley pointed out, that people have used it in time domain for this classification and stuff. Somewhere you can also have like human supervision at the end of the day in the sense, but mostly classifiers that work generally directly on the raw data or like data at the data level in the sense. On the left side, on the right side, I'm not entirely sure what it was trying to say for the most part in the sense. Like I got a feeling that like when I used to write essays as a high school on topics that I did not know about, and when I would like to have to fill the number count, like for example, machine learning helps process and analyze data from large scale structures. I'm not entirely sure what it is talking about in that sense.
Well, we have someone that very much participated in that.
Well, I mean, I would say that, or to put differently, things are either very vague here or debatable in the sense that has it actually been successful in that sense. For example, redshift estimation, like I know there are a lot of papers which are trying to do this for photometric redshifts and stuff, but none of them have actually been like applied on the real data, or people are not really actually thinking about trusting the redshift measurements from these things in that sense. There is always an alternate way of doing it, which people
Certainly an
use.
alternate way of doing it. I think there are examples of photometric redshifts that are being, machine learning based photometric redshifts that are being used in the wild. People are using them. I don't think it's a very detailed problem.
Yep, makes sense. Yeah.
5 fluxes, you have to spit out a number. Okay.
Yeah. Okay, so the one that I wanted to kind of focus on for the rest of the point, because I think that somewhat captures most of the things on this side, was data analysis and simulation. Because at least what Carol and I thought is like, given time, if any breakthroughs actually come from, will be coming from this side, in the sense that like these will be the hard problems to solve going ahead in that setting, I think. But any other thoughts on this slide, if people have, in the sense?
Another thing that should be mentioned for the future is detecting molecules indicative of life in the atmospheres of exoplanets. That's what Mercedes works.
That is, yeah, that was not here, actually, that's true. Okay, so for each of for the data analysis and simulations, we have kind of broken down it into 3 different categories, and we kind of wanted to go by each of them and have people's thoughts on like whether it has been successful, whether it is a well-posed problem or not, and if we can make breakthroughs in that sense. So for example, for the simulation sides, what we have generally is like speeding up of slow simulations. So generally what people want to do with machine learning is that they want to speed up slow simulations. For example, n-body simulations or hydro or black hole simulations in that sense. The second thing that people think about is scaling up these simulations. So for example, you train it on small volume or resolution and you want to simulate it on larger. So for example, there was this great work about like the AI assisted super resolution by Ying here. And the third thing is like using empirical models for subgrid physics in the sense. I'm kind of just running down the list right now. We'll pause at each of them in the next slide, I think. So for inference, the 2 questions that I kind of wanted to touch upon is that like has machine learning enabled completely new analysis in this case? So that's, as was mentioned, that can we use different type of summary statistics, go beyond power spectrum and those kind of things for this, at least in cosmology. I'm pretty sure that there must be other cases in other fields of astronomy. The second question that I would like to come back upon is like, okay, if you do machine learning based inference, is it robust or is it trustworthy? So if you discover some new physics, would people trust, would people believe it in that sense? Or what would it take to convince us that this is the case in this case? And then the third thing that I would like to touch upon in this sense is like, can we learn something new? Has machine learning taught us new physical laws, or can we learn something beyond whatever the training data set that we would have in this case? Okay, so going back one by one about this. So what I've left some space in here in the sense that first I would like to get your thoughts on this, and then I would probably share some of the thoughts that Carol and I came up with about these things. Okay, so simulations, emulators. The question is speeding up slow simulations, scaling up the simulations, and empirical models. Do people think that machine learning has been successful? Is this a well-posed problem in all different settings? Or the way we have been trying to approach this, is that correct, or do we need to rethink things in that sense? So,
how do you know that it follows physics correctly? I mean, it just, it's like a blind kid looking at the machine doesn't use physics to the shortcuts, right? So when you make an analytic model in the days that I was trained before ML, you are trying to simplify the picture by ignoring things that are not so important. Right? But that's not the way the machine learning works. It's not maintaining some thread of physics. It's more about looking for similarities. So are we losing some of the physics? That's my question.
But you also said that you're making, in some sense, some simplification for the things which are probably not important in that sense.
In the old days, decades ago, what humans did was get rid of aspects of the physics that are not as important. right? And simplify, that was called analytic models, where
Yes.
you simplify the picture,
Yep.
like the spherical cow approach.
Yep.
But
In a sense.
the question is here, it's not that way. It's not done by looking at the physics and ignoring elements of the physics that are not important. Instead, it's just going straight to the results, kind of. Yes.
And kind of speaking on the simulations front, as someone who actually runs these simulations, they are fundamentally expensive, and the scales we want to cover to kind of have a representative sample of the universe to do cosmology with is not feasible, and these small scale processes are why we have these subgrid models. Now, in an ideal world, it would be quite cool if we could use something like machine learning to make a bridge between smaller scale things where we can include more physics and actually resolve what's happening slightly more, and have this as a bridge to these larger simulations. However, all of these different aspects are all very expensive, so generating enough training data to be able to do this is not feasible currently, I would argue.
Yeah.
Yeah, so following Javi's question, so it seems to me that that's a super critical question in the sense of like, when you train a model, and excuse my, if I say something that's not correct, because I'm just learning machine learning lingo as well, so. When you train a model, in this case, you're basically feeding it the physics that you know. But then in this case, what might happen is that the model itself gets smart enough that it will produce physical answers for you. So
Yep.
that when like you put in one somehow. And then the question, so to me, this is kind of the equivalent to LLMs, like large whatever models.
Yeah.
Large language models producing these hallucinations. So this is the equivalent in physics, right? This is like you input all the physics that you know, and then how can you guarantee that your machine learning model is not producing a hallucination? I guess so.
That's exactly the point.
And that's hard.
The issue is, can it be controlled in the same way that you control an analytic model, where you understand what you omitted?
Yep.
Like some terms in the equations, you omit them, you know what you did. But in the machine learning, it's sort of vague. You don't know what happened exactly.
I think one of the big issues is it's hard to understand what exactly the neural network does.
Yep.
So hard to interrogate it. When humans develop their models, you can backtrace the assumptions I've made, shortcuts I've made, what is the physical basis for those. With neural network, it's actually difficult to even understand what exactly it's doing.
Can I say one thing just quickly, sorry? So next week, Javier Viana is giving one of the seminars, the CFA seminars, and what he works on is interpretable AI, which basically, that's what he's doing, like trying to develop algorithms that can tell you how they made the decision, and a human can come back and say, oh, so that's what you're doing. So, yeah, so next Tuesday, I think, he's giving a talk at the CFA seminar.
Go ahead.
Yeah, on these criticisms, I would argue this is not about ML. This is about complex systems, right? Because I would argue hydro simulations are not interpretable, right? Oftentimes we have to come up with analytical ways to simplify what the hydro sim outputs look like, right? And be like, oh, I think this depends on density, let's make a few plots. Oh yeah, it does depend on density, but it's also difficult to analyze, right? Because it's a complex system. And I think the way we're moving into it is we need to analyze the data at its full complexity. So analytical models were good when we didn't have the tools or the quality of data to really analyze the full data set, like in cosmology. Analyzing a 3D point cloud of galaxies, which is impossible, right? But now we can do that, so we can phase the model at its full complexity. But this is not an ML problem, right? This is a complex system problem. In terms of ML, whether you can control the system, you can definitely make it follow certain rules, and people work on these things, right? If you want energy to be conserved, you can create a model architecture that conserves energy, right? So there's a lot of work going into how do we add more physics into the simulations. And that's one of the things we wanted to discuss later. You have these two worlds, one that says enough data, big models will learn anything. So if energy has to be conserved, the model will learn to do that. And the other trend is like, well, if we know that's the case, why don't we build models then?
Yeah, but let me give you an example. Energy conserved, let's put that as a constraint. Then there is a tall mountain, and there is a ball at the bottom of the mountain. It can go to the other side of the mountain, and energy will be conserved. But it cannot climb the mountain and do the job. Yet the machine learning would say, oh, energy conserved, this is a valid solution.
But no,
So you have now to think, why did the machine learning do a stupid thing? Which is the hallucination issue that Mercedes was talking about. Because there was a court case where LLM was helping a lawyer, and everything was hallucinated when the court case was filed. And so that ended up being a failure. So the question is, how do we avoid being fooled by a system that doesn't know physics?
That's what you can argue might not be true. The system might know more physics than you think, right? If trained on enough data, it might have learned all these correlations that we as humans learned from the data too, right? So, yeah, I think that's difficult to argue.
Please, Doug.
So I think, first of all, total agreement with Carol is about complexity, and also about obvious that, you know, how do you decide you believe something? What tests do you want it to pass? And this came up even with things much simpler than neural nets, like the Wavelet scattering transform. You want to use that to make a cosmological density field and estimate parameters. What tests do you want that to pass? And you can say, well, we'll run the simulations where we know the answer, and then we'll feed those in, and we'll see if the assertions we get are reasonable, et cetera, et cetera. And if that was good enough for the power spectrum back in the day, and it's good enough for wavelet scattering, like why isn't it good enough for neural nets? I mean, if you have a fairly circumscribed problem like that, where there's some space of simulations you're willing to consider, and you can show that you always get the right answer on those, that was good enough for what we did before. You might argue it's not really ideal. It's not, you know, the universe can still be different than those simulations in very important ways. But that was already a pre-existing unsolved problem that somehow we swept under the rug. So these are all very important questions, but I want to also be a little careful not to set the bar for ML higher than we've always set it for anything else.
I mean, grudges. I mean, it's the same. When you have a graduate student that does a calculation, how do you know that it's right? So the same thing, if the system is very intelligent and it does the calculation, how do you know whether to trust it?
I mean, I think, like, I mean, I would agree with there that mostly you are generally building these simulations for some purpose, right? So you can always interrogate at least those things, and if those things are correct. Say, for example, I'm just estimating the power spectrum here for these things, which is what people were doing. We know that, like, if you run particle mesh simulations, at least in cosmology, they do miss small-scale information. But we still run them because at least on the scales that we are interested in, they give us the correct answer in this case. So if we put the same benchmark for these ML algorithms in that case, and if it is giving you the correct answer for all the statistics or all the metrics that you actually care about, in this case, you have tested that is robust, at least in those regimes. Then does it matter if it is like learning, say, some subgrid models incorrectly in that setting? I think so. And I'm asking this, I'm not saying that this is okay here.
No, if it gives you things you already know about, you didn't discover anything new, so then you didn't gain much from it. The question is, you put it on a new problem, and how do you know whether to trust it?
I think there's an issue of, right, like just you were asking with a graduate student, right?
Yes.
So a graduate student comes to your office and they show you a plot. And you've built intuition over the years to look at it very quickly and query whether it makes sense or not, and what kind of questions to ask, right? The same thing happens here, and you know, I think I've seen this a lot in the area that I'm interested in, time domain astronomy, the use of machine learning for classification. You can very quickly see the difference between work that's done by people that understand the physics and you know how to apply it and how to use it to interpret the results versus something that's done purely from a computer science perspective of I have a problem with classification and people made, I think, pretty serious mistakes in that kind of work. So I think this domain knowledge and having this back and forth. So I don't think it's going to be like one big leap where suddenly you discover something new and you have to take it on faith.
So you're saying supervision by humans is essential.
Yeah.
So that's the key, I guess.
Daniel?
Just to introduce a slightly different idea, when I think about these questions like where am I going to get advantages,
Yep.
the question, I sort of think of it maybe in a multi-dimensional axis, and at least 2 dimensions I would say are the question of how do you verify the answer? How do you verify something's correct, which is the topic we were just talking about. And the other axis is computational advantage.
Yep.
In other words, if I do the machine learning route, am I saving a factor of 3 in compute time? Am I saving a factor of 300? Am I saving a factor of 3 billion?
Yep.
And I think my worry in a lot of the cases that I'm more familiar with in cosmology is that I can see that we can get to a verifiable answer, but I'm worried that we're only gaining a factor of 3 or 10 computational advantage, which is nice, but not really super duper enabling. And then you sort of ask yourself, even if I could verify this thing, is it really worth it to go down this non-standard route? And I'm kind of back to the question that came up again, like what's our AlphaFold moment? To me, it's like, what are the problems that where the computational advantage is not a factor of 3 or 10, but really is a factor of 1 million or 1 billion or 1 trillion, where it's doing something we just couldn't do before. And so, I don't know, I feel like, and of course, but if you're in that world, you can't verify it, then maybe you have your garbage in, garbage out scenario, but I just think, I tend to think of this, like to me, what would be revolutionary is useful applications that are many orders of magnitude computational.
Maybe LSST is a good example, not right? The huge data set, humans cannot digest it, right?
Yeah.
I mean, would that be?
I think it's fair, and an example maybe in cosmology is like the analysis of galaxy SEVs is an expensive problem to do as a forward model, traditional Bayesian statistics problem. We can speed that up if we replace that with a neural net, try to infer that posterior. It comes back to you do a lot of tests to make sure that you really trust that posterior, because you're going to take that at face value as a scientist. But people are working really hard on this, and I think that truly is a factor of at least 1,000 speed up in these tasks.
Yeah.
So maybe like the Turing test, there will be a moment where you would trust the machine more than humans, or I mean, so the question is, when will you get to the point where you trust it more than humans?
I think I'm kind of just agreeing here that you don't trust more than humans. I'm just speeding up the task that I trusted I did well anyways.
Yeah, so that's kind
Yes.
sorry. That's kind of where like the hydro black hole and those things were coming in from, is that like there I can expect more than a factor of 3 gain, hopefully, if I can do this right with machine learning in that sense. But just to keep the discussion going, these were our thoughts in this, and most of them kind of reflect one of the first points that was made, is that especially for the problems where I want a factor of like million gain, in those settings, generally I do not have a training data set to begin with. So in that sense, it becomes a chicken and egg problem. So the whole point of this was to motivate, should we even be thinking about this as an end goal for machine learning in science? Like, does it have to be? Some of the other points that came up and we have discussed is that, like, yes, it might, for example, in the scaling up simulations part, it might not always be a well-posed problem in the sense. Like, for example, you need, at least in cosmology, you need your simulations to be at least some physical size to begin with to capture all the effects. So you cannot just like simulate a very small thing and then scale it up to the end. But that might help with the training data set problem. But most of this, I think we have covered most of the points here. There were some physical symmetries and invariants, which Carol pointed out, that people now do try to throw into these simulations, these machine learning problems, and that is where to capture at least as much physics as you can. If you know that at least it should obey, say, energy conservation, it should be like isotropic, and if you expect those kind of things, so you have equivariances built in to these networks. Most of those things help. But I think overall our takeaway from this was like what Daniel pointed, that like if you want a factor of million gains, you don't have the training data set for any of these things. So that kind of like brings us to question, should we be putting efforts into this? Because there have been a lot of proof of principle papers for this, where people have just trained it on one simulation or something to reproduce something. It's not entirely clear if they will ever lead to anything, at least in the setting, because most of them do not necessarily have a follow-up paper where they go beyond the proof of principle. So yeah, as a community, should this be the focus or not? Was the point. Yeah.
So when you say that a speed up by a factor of 1 million is only a question of training, if it, you know, if you build the architecture and it suddenly discovered, you know, something
Yeah.
inside, you know, new correlation, new physics in play that we didn't realize, right? And it is able to produce results faster by a factor of 1,000,000, then first of all, I think in principle it's possible without huge training data set. And second, I think the key would then be to realize like what exactly it's done, what kind of new insight it has found, and can we, you know, isolate physics related to that insight. And once we found it, maybe we won't need machine learning. We can implement it, you know, that physical insight in our traditional computational.
I would suggest that, I mean, we're probably thinking about different types of problems, but
Yeah.
most of the problems that I feel like people are trying to work on are not things where there's some deep symmetry we have. It's like, you know, you put a billion particles in a box and you actually find it properly, or can you do this hydrosim? Can you input a subgrid galaxy information model in hydrosim? There's no deep miracles in that. It's really just can you beat the mass resolution or you know, big resolution a little bit. Which you know, you can do some of, but I don't think there's a factor for moving.
We mentioned something in response to Avi's concern about incorporating the physics. For those of us interested in gamma ray bursts, are not including what we already knew was physics that we don't fully understand, but something as simple sounding as distinguishing a long gamma ray burst from a short gamma ray burst. Covellia 2, back in 1992, thereabouts, looked at the then available data and fitted two Gaussians to the time of 90% energy emission, T90 as it's been called ever since. And that was the sole difference between if your burst was shorter than 2 seconds, it was a short gamma ray burst. And just as if it was trying to, you know, be consistent with short versus long, and vice versa for long gamma ray bursts. Well, what was left out, and what a paper that I've mentioned in this room a couple of times, I think, by Manaev and Poznanenko. Poznanenko may be a name familiar to more of you. He's a key player in the SRG mission. But in any case, what this Manaev Poznanenko paper did was to complain about what I just mentioned, that it isn't just a time duration. There's a fundamental difference in luminosity. When you have redshifts for short GRBs and long GRBs, apart from uncertainty still in beam angles, which have their own way of being measured, it was found that the long gamma ray bursts are much more energetic. The luminosity is typically a factor of 100 larger than a comparable duration short GRB. And there have been some peculiar long GRBs by the original definition that showed evidence, at least one, I don't remember the GRB telephone number, but some of you, maybe Guido remembers it, that this long GRB produced not just the normal afterglow that both short and long GRBs have when the beam is plowing into the interstellar medium, depositing energy, but there was evidence in that what you might have thought was an afterglow that this was a kilonova, that there were elements being created. Our process that up till now we only have really seen in one short GRB, 1717. So the bottom line here is there is, I think, real physics being included in this relatively, you know, yes/no question of short versus long. And by incorporating parameters that are basically dependent on the spectrum, you can, and this is what we want to do for a mission that we hope to propose in 2025, if that matters here, you can, in principle, from the GRB alone, from its spectrum and its time variability, original cut, you can predict redshifts, and that's what we're after. Because if you can do that, and you can get to a given probability, a constraint on the redshift, and when you have anything that looks like a redshift greater than just make up a number, well, not make up. The current maximum redshift of any GRB is 9. Z equals 9. You can correct me if I'm forgetting the burst that's greater, but roughly that. What we want to do, and what lots of people have talked about, including Avi, who began this discussion back in the 90s with Volker Braun, you can, with GRBs in principle, if you can predict the redshift, measure top 3 stars, where they are, at what redshift did they turn on. So anyway, this I think is a demonstration of something that really needs more thought, and we're going to work on an ML simulation to try to do what I just mentioned. If anybody wants to chip in, we would be happy to have more colleagues involved.
Can I just say something about the emulator part? Because I probably don't know enough about inference, but with respect to the emulators, I mean, and whether they can help in uncovering new physics, I mean, I think the answer is no. I mean, I think they can help in 2 ways. Either because they really speed things up, you know, so that we don't have to run that many simulations to understand things, or because the output parameter space of the output from the simulations is large enough, and then the machine learning can find correlations that we wouldn't know. But the way I think about an emulator is really like a very complex sort of nonlinear interpolator. So you will always be facing the problem of, you know, how fine do I need to make my simulations in order, if there's something that happens between 2 points, 2 grid points in your simulation, I don't think the machine learning is ever going to learn it. I don't know if there's studies that show that it could. I just don't see how. And I should be more positive about machine learning, because we're trying to get a proposal accepted for it. In the particular case of the simulators, I don't, maybe you guys know more about this, but is there evidence that a machine learning model can learn things that happen between points of a grid in a simulation?
I think yes. So the point here was, I agree with you with your first point in that this was the point here was not to learn new physics. That was just to speed up things for the emulators. I think there's a fair bit of evidence that, like, yes, you cannot. You have to have some fineness to the grid, and as you go to higher dimension spaces, like higher dimension parameter spaces, the number of simulations that you would need to train the emulator would increase. Yes. And it increases quite rapidly. So you cannot, it increases quite rapidly as you go to the higher dimensions, because as it scales not exponentially, but you don't need to, it doesn't scale exponentially because you have better space filling points that you can pick up. But I think I would say yes, that it does, people have tested that between the points, it does give you correct results and stuff. In fact, most of these things are validated with the points which are not used for training in that sense.
2 more comments.
Yeah.
Go ahead.
Okay. So, about the super resolution, I'm really skeptical about this. And it's not because it's something completely unrelated to simulations. Maybe many of you have seen this wonderful example when a neural network that is supposed to recover super resolution from pixelated images was fed with a pixelated image of Barack Obama, and it reconstructed a face that looked like a white man because it was trained on white men's photographs. And this was completely wrong. And this was like, this initiated a lot of discussions about, you know, like ethical and so on and so forth.
Yeah.
But related to this, what you are getting as a super resolution might have nothing to do with the reality, in fact, because it depends on how you train the system.
So I wouldn't necessarily say that for super resolution, but that I think holds true for any and all of these approaches, that like your training, the way you set up your training data basically sets up a prior distribution for whatever you're going to learn. So that is called training data, like that does bias your results in that sense. And completely agreed, like that is, you need to be careful about your training data in that sense for this. Yeah.
Can I actually tie it back to the original slide before we discussed whether machine learning is going to be revolutionary for astrophysics? So I think we discussed a lot about whether machine learning, how can it be trusted or not. But I think what the 2 examples of where you showed that machine learning really was a revolution, is actually where the case where the pure raw performance was just so good that even if you can't trust it, sometimes it still is just revolutionary. So I think the question should be really, are there problems in astrophysics where there's just no good solution so that you would, in reality, use a machine learning solution just because it works so well? And I think that is the case because if the reason people like in protein folding use actually AlphaFold is actually because it just gives so good results. Sometimes they're trash, but they look at it and then they don't use it. But
so is there an unsolved problem that is just too difficult for us? Is there something like that in astrophysics? Does anyone know about it?
Microphones work. We're already found
What is it?
How microphones work.
I mean, obviously there are issues like what is the dark matter, but that's not a well-defined calculational problem. I mean, in quantum mechanics you have like calculating path integrals that are very complicated, and protein folding could have been phrased in that way. Is there a problem that is too complex for us to solve? Does anyone know of a problem like that?
Well, yeah, I mean, it's all these problems that involve just gigantic dynamic scales. So molecular clouds and star formation, where you have this just enormous range of scales, and you're not going to get to a, 10 to 30 bytes of data to actually characterize it. So if there's some way to cleverly span that, or another example would be turbulence sort of effects.
So you can approach it in the same way that statistical physics. You could have argued that you need to know the atoms, the motion. You need to simulate the motions for the atoms to figure out how a fluid works. And then statistical physics and fluid mechanics came along and simplified it. So in a way, is there a way for a shortcut? That's the question.
No, I think that's right. I think you need to find a different representation.
Right.
That's effectively what you're saying. That you can't. Thinking in cosmology, like I showed you a picture of dark matter halo. Your eye sees a dark matter halo with a shape and that C profile. The computer sees 10 to the 7 base positions.
Right.
Not the same representation. So if there's a way to somehow, and that's a trivial example, but ways to learn things that help you with a multi-scale problem by changing the representation, maybe you would have to.
Yeah. And one other example is Fourier space. Sometimes you can solve problems in Fourier space.
This is like a perfect way of thinking about it, is that a neural net can help you if you have no good physical intuition for the basis set to select. A neural net can help you do that, and that's a way that you can
Like principal components, finding the essential.
basically, but non-linear,
Carol, go ahead.
Yeah, I just wanted to close this with the fact that I think for emulators, well, first of all, in terms of like learning new physics, I think they are related ultimately to learning new physics, right? By exploiting the signal to noise. If you can really model the whole data set that you want to analyze, which you can view through simulations, then hopefully you can extract more signal to noise, right, and find significant deviations, right, between data sets. Like in cosmology, we have all the extensions, but there are tensions. Can we make them actually statistically significant? Emulators could do that. But I'm still mind blown by the fact that I can't run a hydro simulation on my phone with machine learning. I always thought we would be there, right? We're not. We're very far away from that. We're not even speeding up by a factor of 10. We're not doing it. Like, there's no machine learning powered simulations, not even embodied simulations that are actually used. And I think that's interesting. If all it takes is large data sets, we could come up with a massive grant, right? Run a huge data set, train the model that will do that, right? For hydrosims, I think it's more complex because we don't really know how to do hydrosims. So we're trying to solve two problems at once, right? You have the hydrosim that is all made up, and you want to replace it by a model that would make it even more up, right? We've talked about this before, Jake. It's also difficult to treat the hydrosims and stuff, right? That's why I think the multi-scale problem could be a more interesting avenue for machine learning, right? Because all the separate models in hydro simulations are made up, or are some analytical models that we've fitted to data. Can we really use this to learn something new but bridging scales, right? That would be, in a way, learning new physics by really modeling the interactions between small and large scales, right? But of course, it's also a complex problem.
Ramesh, go ahead.
So yeah, I mean, I'm no expert on physics. That's why I didn't open my mouth. But let's say that there is some real complex, enormous multidimensional, nonlinear problem, and your machine learning just produced this fantastic result, something, right? And of course, I want to convert it into an understanding, What is it telling me? Why did this happen? What's the physics behind it, right? So if I'm faced with this problem, what I can't get my head around is the following. Should I then go and come up with my own spherical curve models and see what is the reason? What exactly was happening here? What might it be? Is it the third order correlation function because I'm only thinking in terms of second order? Should I do that offline as a theorist? Or is there a way of digging into what the machine learning guy did and opening it up and saying, you tell me, what is this? Where did this result come from? I'm not clear which is the right path.
I would say it kind of depends on how you, so a lot of times, especially in the physical symmetries and invariances thing, that people do somehow try to pose that thing inbuilt in the model so that you don't have to go and post ad hoc, ask these questions. Sometimes you can interrogate some of the components. So for example, there were works where they essentially trained a simulator, like a deep network, to do the simulation. And then to interpret what it was doing, they essentially changed the input data and gave very specially designed input data to see how the network resulted in that, to get this is basically called a response analysis, to see how the network responds to this input data and the other thing. And that gives you some insights about how it is doing. So I think it kind of comes down to what exactly, how you want, or in how much detail do you want. And then it also comes down to the question how much do you actually end up learning about this in that sense.
That's an experimental approach, okay?
Yes.
So you can say, if you learn this knob, what to
It is both. It is that is one way of doing it, which is how some people do it. Sometimes people just build some things into their architecture, for example, with the symmetries. And sometimes you have some components that you can just see. So for example, there was this one paper which was trying to correct for the small scale forces in the simulation, and there they could actually go and look at what my kernels that the network learned look like, and they could see that it is not doing anything on the large scales, it is not doing anything on the small scales, and it is the intermediate scales where it is adding some force, which kind of aligned with their physical intuition in that sense, that this is what I expected it to do and this is what it ended up doing. That builds some confidence in what you're doing. Now, exact function form of that kernel that it learned is probably not what, in some sense, it's not that meaningful. That, why it is a to the power 1 or a to the power 1.2 or 1.3 in that sense. You don't really gain anything from that, at least physically speaking. What mattered for them was in the end that, it didn't add corrections on the large scales where I expected it not to, in that sense. So that's what I'm saying. It kind of comes down to in what detail do you want to interpret what it has done.
Okay, we got to our time limit. We just
yeah.
Because in half an hour we have also the lunch.
Right. So I don't think I'll be able to go through any of this.
That's okay. We had a very good discussion.
Yeah. I'll just.
Of course, there is always nature, right? We don't need to do any simulation.
Yeah.
We just look at nature, and Ramesh would analyze it similarly.
Okay. In the interest of time, I can briefly just flash through the slides in 2 minutes and close it in that sense, or.
Well, anyone that needs to leave can leave now, but because we have in half an hour another.
Sure.
4.
Okay. So the next question was inference. The question was, has ML enabled any new analysis? And if we do the robustness analysis, what we wanted to point out here was that in principle, ML has enabled new analysis with simulation-based inference, but the challenge again there was you need simulations. Differentiable modeling is a different kind of thing that has come about. It is not machine learning, but it is robust, but it is just because of the technical advances that machine learning has done in the industry, we can use that. Regarding if it is robust, it ended up coming down to how much do you trust our simulations? And the question, one thing that would have been interesting to discuss is that if you learn something new, how do you actually validate it? Because if you need to go back to your standard analysis to validate any new physical discovery, then is there any motivation for doing it in the first place? The other questions were, do we learn something new? Can we learn new physical laws? And can we learn something beyond the training data set? People are thinking of symbolic regression or interpretability models, which is what Ramesh was talking about. It's unclear how much do people actually learn, if symbolic regression is just a fitting formula or you actually learn physics. And regarding the beyond the training data set, anomaly detection is something that people look into. Because I'm no expert on that, I wanted to ask people if it has been useful. There has been some work on learning generative models directly from the data. So for example, just taking the galaxy images that we have from Hubble and stuff and just learning generative model to reproduce those. Again, you don't really learn anything, but people have used those as priors, as well-defined data-driven priors for their analysis, which can be useful in that sense. This was something we wanted to discuss about data science versus inductive biases. So what I showed in the beginning is that most of the successes in industry have been driven by increasing compute, data sizes, and parameters, while in science, people mostly focus on inductive biases, training on small simulated high-quality data. Is there a way we can combine the two paradigms to make these successes? And then some questions on what we are limited by. Lack of training data is something that came up, lack of funding, if there are things. In Astro, we generally are not able to run experiments. We have only one data set, which is a limitation, which is not there in other sciences. And how much do we focus on interpretability and understanding, which came up a lot of times. Some other things we wanted to touch upon, these are kind of sociological aspects of things, is that a lot of works have just focused on proof of principle exercises. Someone mentioned about this, is that ML is oversold in astronomy, so that was touching upon that. And structural issues in academia was basically that doing machine learning in astronomy is hard. It's an engineering problem at the end of the day. And if you really want to make progress, so this is where the DeepMind thing came back. AlphaFold DeepMind thing was coming back, is that to drive those innovations, it came from DeepMind, it didn't come from any university. And so do we need to rethink things in academia for that if we want to drive those innovations in sciences in academia? Okay, these were some of the points about what we can do, what we should do, and things. Some of the things are happening right now here. Some things that we might want to, for example, funding in AI-specific centers, collaboration with industries. Maybe as a community, we should think about high-quality data sets which serve for the whole community so that you don't have to have one institute working on those things. And some of the new problems that we should be discussing, which I think we have discussed quite a lot about what kind of problems should we focus ML on. But yeah, those were broadly the points that I think. This is, I think, the last slide. Yeah, I think. Cool. Thanks.